Right, today we're going to continue our discussion on derivatives by talking about Rolle's theorem and the mean value theorem. So we're going to start with the statement of Rolle's theorem. Rolle's theorem says that if f is a function which is continuous on the closed interval a, b, and differentiable on the open interval a, b, and f of a is equal to f of b, then there exists some number c in AB such that the derivative evaluated at c is equal to 0. So what this is saying is if we have a function that is continuous, meaning you can draw it without lifting your pencil up, and it's differentiable on the open interval, so there's no sharp corners or breaks or anything like that, then somewhere in between a and b, as long as the endpoints have the same y value as well, somewhere in between a and b, there's going to be a point where the derivative is 0. This means that we have some critical value in the interval, and thus we're probably going to have a maximum or a minimum value from the material that we learned recently. So I'm not going to prove Rolle's theorem for us today, but I am going to draw a couple pictures to convince you that this is a true statement. So here's an interval a to b, and I'm just going to draw a very basic example first. There's f of a, f of b, and I'm just going to have a nice boring function, a nice horizontal line. So let's just say that's our function f. It's continuous on AB and it's differentiable on the open interval AB because there's no sharp corners. Is there a point C somewhere between A and B where the derivative is equal to 0? Yeah, there's a lot of places where that's true. I'm just going to pick one of them. Here's a C where that's true because the tangent line f at C is horizontal because the entire thing is already horizontal. So that's a very basic example showing it's true. Of course, you're going to want something more complicated to convince you that this theorem is always true. So here's another example. We still have f of a equals f of b. Let me draw some other continuous differentiable function. We'll use that guy right there. Is there a value between a and b where the derivative is equal to 0? So I'm asking, is there any place where the tangent line is horizontal? And yes, there's a couple places. I have this point here up at the top. My tangent line is horizontal, so this C could be a possible value. And also down here, I have a horizontal tangent line. So that number C also satisfies Rolle's theorem. And just one more example to convince you. Let me just draw one more continuous and differentiable function. This one doesn't have as many bumps, but it's okay because there's still that value. This would be my C, where the tangent line is horizontal. So it seems like this would be a true statement. So we're going to do an example where we actually use Rolle's theorem to prove something about a function. So our example says, prove that the function x to the third plus x minus 1 has exactly one real root. Well, first, to prove this, I'm going to first point out that we definitely have at least one real root. Think about what the graph of this function would look like. All of our cubic polynomials have the same general shape. Something like that. It could be bumpier, it could be stretched out more, but the important thing is it's going down to infinity forever on one side and up to infinity forever on the other side. So at some point, it's going to touch my x-axis, meaning that it's going to have at least one root, the place where it crosses the x-axis. So I know that I have a root. So we have at least one real root, since our function is continuous. And when I look at what happens when I go to the left side of the function, I'm down at negative infinity. And when I look at what happens on the far right side, I go to positive infinity. So at some point in there, I'm going to have to cross the x-axis, and so I'm going to have a root. But I need to show that there is exactly one real root, and all I know is that there is one, but what if I have 2 or 3? We know we can't have more than 3 because it's a cubic polynomial, but there's nothing just looking at this that tells me I have to only have 1. I could have 2 or 3. So let's just assume that we have more than 1. So assume we have more than one root. So I'm going to call them, so f of a is 0 and f of b is 0. Well, then I have my function is defined to be exactly the same at both a and b. My function's a polynomial. So that means it's continuous on this AB and differentiable on AB. Well, this tells me by Rolle's theorem there should be a C in AB such that f prime of C is equal to 0. But for our function, remember our function was x to the third plus x minus 1. What is the derivative equal to? Well, using the power rule, our derivative is 3x squared plus 1. And is that ever going to be 0? No, it's not. This derivative is never 0 because no matter what I plug in for x, this 3x squared is going to be something that's not negative. It's either going to be 0 or a positive number. And then I'm adding 1 to it, so there's no way this derivative can be 0. So we have a contradiction. So our contradiction is against our assumption that there was more than one root. So therefore, there's only one root. And that's the end of our little proof there. So this was just a standard proof technique called a proof by contradiction, where you assume the opposite of what you want to be true, and then show that if that were true, some sort of problem would come up. And we use Rolle's theorem to get the problem that would happen with more than one root. So now we're going to move on to talk about the mean value theorem. The mean value theorem is a pretty important theorem. And the mean value theorem says we're going to let f be a function which is continuous on the closed interval a, b, and differentiable on the open interval a, b. Then there exists a c in our interval a, b such that f prime of c is equal to f of b minus f of a over b minus a. So what this is saying is if you have a continuous function, which is also differentiable, at least on that open interval, then somewhere in that interval, there is a value for which the instantaneous rate of change is exactly equal to the average rate of change on the interval. And I would also like to point out that Rolle's theorem that we just learned is actually a special case of this mean value theorem. Because with Rolle's theorem, we had f of a equals f of b, meaning this average rate of change over here would be a 0 over b minus a, which is 0. And my f prime of c would equal 0. That was the statement of Rolle's theorem. Mean value theorem is a bit more general. So let me draw a picture representing this mean value theorem and what's going on there. And then we'll do an example using this. So here's a graph, A and B for my interval. And I'll say here's where f of A is. And let's say this is where f of B is. And there's a nice continuous differentiable function. Except I made mine a little too curvy over there, so it wasn't really a function. Let me try to make that a little bit better so it passes the vertical line test. There. Something like that. We'll say that is my function. Then, if I were to connect these 2 points here, that line has slope f of b minus f of a over b minus a. And my mean value theorem is saying that there's some value c where the derivative, which gives the slope of the tangent line, is going to be equal to this exact same value over here. In other words, there's a place in between a and b where the tangent line is going to be parallel to this line connecting those 2 endpoints. And that would be right about here. If I draw the tangent line right there, there's my x value c, and that tangent line is parallel to the line that's connecting my endpoints of the interval. So this is just a picture representing what's going on in the mean value theorem. It's not actually a proof, it just shows it for this one exact example, but hopefully that helps convince you that it is a true statement. Let's do an example using this mean value theorem. All right, we have let's let f of x equal x to the third minus x. And we're going to have a equals 0 and b equals 2. the mean value theorem says that there's going to be a C in the interval 0, 2, such that my f prime of C is equal to f of B minus f of A over B minus A. And we're going to find what is this C. So to find the C that actually comes with the conclusion of the mean value theorem, all we have to do is, on one side of this equation, we're going to find the derivative and we're going to plug C into it. And over on this other side, we're going to find our f of B and our f of A and divide it by B minus A. And then we have an equation to solve to find C. So let's set this up. My f of x was x cubed minus x. A is 0 and B is 2. So let me just write down those couple of things that I need. F of x is x cubed minus x. B is 2. A is 0. And we will need the derivative. So let's just find this derivative real quick using the power rule. 3x squared minus 1. So let's set up the conclusion from the mean value theorem and try to find the C. I have f prime of C equals f of B minus f of A over B minus A. F prime of C would be 3c squared minus 1. F of B, well, that's what I get when I plug a 2 into my function. F of A is what I get when I plug 0 into my function, and B minus A would be 2 minus 0. So I have 3c squared minus 1 equals 2 to the third is 8, minus 2 is 6, all of that's 0, so I have 6 over 2. And this is the equation I need to solve to find my C. Once I solve that, I'll have the C that satisfies the conclusion for the mean value theorem. So let's solve this. Let me simplify that 6 over 2. That happens to be 3. And then I would add 1 to the other side and divide by 3. Then to find my C value, I just have to take a square root. And we know when we take a square root, technically we need to do plus or minus our square root. So I get plus or minus the square root of 4/3. Well, I'm supposed to have a C in the interval 0, 2, so I'm not going to need the negative root, but the positive root is in that interval. So C equals the positive square root of 4 over 3, which is the same thing as 2 over the square root of 3. And this is the value for C that satisfies the conclusion of the mean value theorem. So if you have to find the C that satisfies that conclusion, just plug in all the stuff you know into that conclusion and do some algebra, and you'll find your C value. So to finish up this section, I'm just going to quick write down a couple of extra facts that we get from the mean value theorem. So one extra fact that we get, one extra theorem, is if f prime is equal to 0 for all x in the interval AB, then the function f of x is constant on AB. So if you know that the derivative is always 0 on an interval, then the function is constant on that interval. That kind of makes sense because we already know the derivative of a constant is 0. So this logically makes sense. And this follows from the mean value theorem. And one other corollary that we get from the mean value theorem, if f prime is equal to g prime for all x in some interval a, b, then f of x minus g of x is constant. On that interval. And that means that f of x is going to be equal to g of x plus some constant c. And this also makes sense in general. If I have f of x equals g of x plus c, well then f prime of x would be equal to g prime of x plus the derivative of that constant. The derivative of the constant is 0, so I would get f prime equals g prime. The conclusion makes sense. So both of those are actually facts that follow from the mean value theorem. And that's about it for this video today. It's just to get us some practice with some of the theory behind the mean value theorem. And we will continue our discussions on our future videos, and we're going to be moving very soon into something completely different. Instead of doing derivatives all the time like we've been doing pretty much all semester, we're going to start undoing our derivatives, something called an antiderivative or integration. We get to start that just already next week. So I hope you come back to watch those videos. If you have any questions, leave a comment down below. If you're one of my current students, feel free to send those questions through email or in office hours as well. And I will see you all the next time.